This is the IEEE Computer Society Distinguished Lecturer webinar series brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors around the world who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Hi, everyone, and thank you for joining us today. Our apologies for starting a few minutes late. My name is Scott Levine. I am the IEEE Computer Society Membership Manager. And with us today, we have Ann Elster, who's going to present AI for HPC experience and opportunities. A few housekeeping items. If you have any questions, please enter them into the chat. We will get to as many questions as we can. You will be emailed the slides and the recording tomorrow. And I think with that, we will get going. And the floor is yours.
Thank you, and welcome to this webinar series. I'm sitting here in Norway in a nice afternoon in a very kind of windy, stormy day. Hope you have a nice weather, or at least a nice time wherever you are in these crazy times. I'm Ann Elster, and I'm a professor at NTNU, Norwegian University of Science and Technology in Norway, here in Trondheim. But I'm also associated as a visitor and have been for many years at the University of Texas at Austin. Did not advance? Yes. So that's here you see a picture of our campus in Trondheim, as well as the tower at UT. I've been doing GPU computing for a long time, promoted through the technical committee at supercomputing, the first tutorial for CUDA programming. I think that was back in 2007, and we started even before CUDA in my group. And I was a PI for both the teaching center and research centers for Nvidia when they had those programs in the early days. Of course, I couldn't do this presentation or most presentations without the efforts and great help from my research groups and collaborators. And here you see us. Usually we have I now show a group pictures, but because of COVID, we now tend to have Zoom meetings, right? So here's the Zoom meetings of some of my graduate students and collaborators, including a visiting graduate student from University of Aarhus, Jørgensen, and also a colleague who used to be at UT San Antonio and still affiliated there, but is zooming in with us from Greece, and my postdoc, or incoming postdoc, Ajit, zooming in from India. So we're quite an international group. And of course, there's many students also that have been with my lab through the years that have influenced the work we do. And here are some of the more recent pictures. In fact, the light is, this is it's Fredrik Kjølstad visiting us. He used to be here in Trondheim, came in as a bachelor student, took a bachelor's degree in Gjøvik, and then worked for ARM here in Trondheim, and then decided to take my parallel computing class, and wanted to study to the US. And so he's my sort of pride and joy, because then he went on to study with Mark Sneer at the University of Illinois. And Mark and I served on the MPI Standards Committee. And then he went on to finish his PhD at MIT and just started last year at assistant professor at Stanford. So proud of him. And it gives us great relationships to a lot of people throughout the world. We also have this big new project started here at NTNU that I'm part of, which is known as the Center for Geophysical Modeling. And that's one of the big application areas, of course, in Norway. It shouldn't be a big surprise that Norway, being an oil nation, is well known for their geophysical modeling. We have a lot of North Sea oil, and there's a lot of research over many years. So we have a world-renowned group in that area. And so, of course, it's also a great source of funding. And this project is trying to take that technology in Norway's cutting edge on and apply it to onshore applications. You know, these days with climate change, you know, there's avalanche forecasting, earthquake forecasting, anything like that, many things like that, that we're trying to take the technology that was developed for cutting edge for the oil industry and apply it to, problems that we want to solve. We definitely have some more challenges of the earth with the clays, and Norway, it makes it right around Trondheim. There's a lot of clay, so people worry about mudslides and things like that. We also have collaboration with the medical groups at St. Olav, our local university hospital, and also other medical organizations. Aging population, obviously, big push both here and at the Newdale Center at UT Austin. And of course, I collaborate with other people within NTNU as well. Like I mentioned, we have this new center for geophysical forecasting. And in fact, we just announced the last few weeks that new 11 PhD positions, which are paid pretty well here in Norway. Of course, costs are high, but we pay them pretty well. And if you have any students that want to try a PhD, or if you are a student looking for a PhD position, you should go to this website or just search on us or contact me after this talk. Now, what is this talk about? So notice it said AI for HPC. That is not the same as HPC for AI, which is most of the people think about, right? Because current AI or machine learning in particularly rely on a lot of compute power, meaning things that are like HPC. But how can AI itself help HPC as a field? And that's what we're going to look at here. And here you see this box we got back in December 2018. It's known as the Nvidia Dgx2. It has 16 GPUs, which is graphic processing units. That originally were thought of as gaming cards, but now are thought of as AI cards. They have put them in an all-to-all switch, known as NV switch, which means they had a high bandwidth interconnect between the GPUs. And of course, they dress it up with a lot of software that is particularly targeted AI applications. Now, our question is, how can this box also be very useful for traditional HPC applications, including things you in the olden days needed supercomputers for? Now, one thing you can do is use AI techniques for code optimization and data pruning. The data pruning, pruning of data is sort of, a lot of people will say a lot of machine learning these days is just a glorified form of data mining, trying to find, patterns and pruning down the data to find the information you want. You can also use these kinds of techniques for code optimization that's we've been looking at in my group for some years now. Still not there perfectly yet, but we have some interesting cases. And that is because when you're trying to target very complex computer architectures, it's a lot of work to try to move your code and auto-tune it or manually tune it for any given architecture. And when it comes to GPUs, they tend to change every 6 months. And you really don't want to recode, large applications that often. So you need to have some kind of parameterization. And if you can do that parameterization, that opens up for using AI techniques. Another area where you try to apply this is that in a GPU compute, that's really we're now these days working for AI, is for this full wavefront inversion that is used in a lot of different seismic codes or earthquake simulations. This is a tool that can build accurate velocity models by refining and minimizing the difference between recorded data and what's modeled. And so you do like, that's why it's called forward inversion. Now, current world scale models are actually run on the summit. I give a picture of it later, which, okay, this year it's not the largest, but was the largest supercomputing, I think, last year, right? So this year is now the Japanese one. But, not all of us have access to the world's largest supercomputer. So it's nice to be able to do some of these things more locally. Now, why do we worry so much about these parallel computing in general? Is because we hit the power wall. It used to be until about 2005, that we could just wait 1 year and the frequency of the processor would double. So when you ran your code next year, it'd run twice as fast. Well, that just petered out around 2005. We basically have not seen processors go higher than 3 to 5 gigahertz since that time. And of course, there are many reasons for that, but the main one is the power wall. Basically, the chip density still continues to increase, but it also has this problem when you clock up the frequency, you have this power squared, which make it extremely hot. I mean, already it's hotter than a hot plate. And, basically looking at, nuclear reactor type temperatures if you were to continue that curve. So what one did to circumvent that is increase the number of processor cores instead. And of course, that means you now have to figure out how to use all these processor cores in parallel. And notice that even your smartphone, whether you have an iPhone or an Android, they are actually multi-core processors with GPU chips, which has separate chips for graphics processing. And to take advantage of all this parallelism, you need to expose it to and needed to manage it by software. So this is the area that I've actually been working in for quite some time. Of course, we didn't think of it as something we do on the smartphone. We didn't even have smartphones back in the 1980s. But we did have it dabbled around in concurrent and parallel Pascal while I was still in college. And in 1986, I worked on the Intel Hypercube. We had the first one outside of the US in Bergen, Norway at the Christian Michelsen Institute. And we also had, it was also the same year that the first supercomputer, the Cray 1, came to Cray XMP came to here to NTNU. In 1987, I was at the IBM research at Yorktown and got to use 4 3090 vector machines all at the same time. At the time, each of those were thought of as a supercomputer. So that's probably the only time I got to use that many percentage of the world's compute power, right? Because since then, compute power has sort of grown exponentially everywhere. There were Intel Hypercubes, later versions at Cornell when I was a PhD student. And my actual thesis was written on something called the Kendall Square Research Machine, which actually was a great machine, but the company went under for, some financial issues. They were also, just Schlumberger, there were SGI systems. But then, since the era of cluster computing, we're using commercial off-the-shelf processors, although the Intel IPSC, Intel Personal Supercomputer, as it's known as. And I say that with great joy because Nvidia claims they are the first supercomputer, but Intel said that back in the days. They were, the first to be constructed off the commercial off-the-shelf chips, or COTS, as you like to call them. And this means that you use the same processor that you use in more of a general application, not special purpose processors targeting HPC. That's sort of, which was the case when we had the craze, right? They really were targeting that market. And the vector units on the 3090s, similarly so. The IBM supercomputer Nord we got here back in 2006, we were happy to, came in at 7 teraflops. As you'll find, this is actually not that uncommon for high-end graphics cards. The GPU, how to program the GPUs was initially extremely hard. You had to sort of rewrite your codes into a very graphics-like language, usually annotated like CG, until CUDA came with their programming language, as well as AMD with the close to the metal around 2006. And now these big boxes are sort of retargeted AI. But the first motivation for GPU computing came from the processor science because of the emerging gaming market. There'll seem to be enough of you, or at least maybe not you, maybe somebody you know that likes to play computer games, and they want them as realistic as possible. In order to accommodate that, there were a lot of engineering going into making really cool processors. And that market was growing more than the computer market, other computer processing markets. So there was a lot of sort of innovation going into those designs. Nvidia came with their first GPU in 1999. And in 2006, like I mentioned, the close to the metal and CUDA environments came. And here at NTNU, we took a wavelet application and sped it up 40 times by running it on the graphics card, just a GTX 8800. My colleagues first, when I bought the card, thought I was a little easy to be manipulated by my students, as I used such a large budget, over $500 or $600 or whatever it was, more money back then, on what seemed to them like a computing toy. But we showed with this 40x speed up, it could really be used for real-time applications such as my ultrasound. And today, there isn't an ultrasound machine out there, I don't think, at least not the big ones they have at the hospital, that are not using GPU technology. Also, you'll notice that this top 500, the biggest supercomputers in the world, started using GPUs extensively in 2010. And here's the picture again of the box. I said this is one of our sysadmins when he's installing it. And you notice that it has 2 petaflops performance. And that's petaflops, not teraflops performance inside this box. Now, the new one that was announced last year, the Dgx2 actually comes in at 5 or 7 petaflops. And the nice thing about that processor, it actually has 80 gigabytes, at least the one announced for April this year. And then the kind of interesting part for using AI for HPC is that this is the first time the tensor core processing units that were targeting those tensor-based computes, those small little matrices you use in AI, come now for 32-bit floating point. And that's brand new this year. And that makes them even more interesting, right? We also in my lab have an IBM power system, model AC922. That's the same architecture that's in sort of one node of the Summit, except for they don't have, they have actually 6 Nvidia Tesla B100 and have a better cooling system, and then have quite a few thousand of these. And here you see the picture of the Summit, pictured here 2019. As you can see, they have 9,216 of these power 22-core CPUs and 27,648 Tesla cards. So that's a little more than most of us can afford and have access to. Of course, the power it consumes is 13 megawatts and has 250 petabytes of storage and runs at 200 petaflop peak. A new machine in Japan is actually over 500 teraflop peak and is based on the ARM architecture that originates here in Europe. And their GPU part of the ARM is made here in Trondheim, a spin-off from my university here. So we're kind of proud of that. Now coming this year is the new Lumi system in Finland. And it's actually going to be faster than the one in Japan, but they still may be beaten by others by the time they sum them up for supercomputing. So there's a lot of interesting architectures out there. And that one is based on, it's by Ethos, actually stems from the Bull, that company that was started by Norwegian back in the 30s as a competitor to the precursor to IBM. And then the long story ended up as Bull Ethos. And that's going to deliver this new supercomputing in Finland that will be AMD-based with the new AMD processors along with the new AMD graphics cards. Now, the question, though, is how do we program these for performance? You know, how do we, how can we use them properly? And I like to say there are three key things if you want to do parallel programming for performance. And the number one is you want to keep those registers busy. You don't want you forget what's on disk, or your storage or in memory. You really want to, if you really want to go for performance, you need to keep your register units or your register or your pipelines on the processors busy. That means you need to take care of caching, and you really should be reducing memory accesses. And you have to consider sometimes it may be even if you don't need full run-length encoding, if you can get away with some compression that's fast, like cosine-based transforms, you may be able to find that reducing the memory traffic by compressing the data back and forth, especially off the disk and into memory, could actually be feasible. It's worth considering. But number one is keep those registers busy. The second idea, you see this coming with big data, is to move the compute to the data, because the data itself takes so much time. When it's huge data sets, takes so much time to transfer and also energy. So notice the big supercomputer using 13 megawatts. Well, it's actually expensive to keep moving a lot of data. So you want to move the compute and maybe prune the data. This is especially true when you do edge computing. You see this, for instance, at CERN, where they have special purpose FPGAs sitting on their experiments and pruning the data before they even start storing them, because otherwise they will have way too much data and it will take too much energy and just won't have the capacity to do it. And of course, this computer science basics still apply. You still need to pick the right algorithm. It's not, there is a reason why FFT is still the most used algorithm out there. They still use it for partial differential equations when you can. I mean, the boundary conditions are nice and you can do a fast solve, elliptic electric solver as they're known as. You still use it for your DSP processing, to do signal processing, which is, of course, its original application. And whenever you, often you see it in statistics and other, if you can use a fast algorithm, not only the FFT, of course, but a fast algorithm, that, of course, matters. The tricky thing is if that algorithm is also tricky or especially have a lot of tail recursion, it may not parallelize well. And that often in parallel computing, a simple algorithm, even though it's not serially the fastest, may be better algorithm for parallelism. One of these cases of this is you saw the successive over relaxation solver for partial difference equation, the SOR method, had a renaissance in the 80s when parallel computing came sort of last time. It has a big wave. And that, although it was done in the 50s and 60s or 60s, then it showed that it was very good. If you could do a red-black ordering and structure your data well, it was a very good solver, even though there were much fancier and seemingly faster solvers, at least for serial machines. But as you know, today, you don't have a serial processor. Like I said, even your smartphone has multi-cores and GPUs. This is all the bottom. You really are like in real estate. It boils down to the challenge of data locality. So that's one slogan that my students always remember from this class. And I said, to be a performance architect or a good parallel programmer, you need to really consider three things only, and that's location of data, location of the data, and location of the data. So location, location, and location. For those of you from the US, you will recognize this slogan from the real estate agents that will say the pricing of housing is strongly related to the location of your property, right? It's a big difference whether you have an apartment in New York or an apartment out in, some faraway place all by itself. In a duplex, for instance, in a deserted place. There's a huge price difference, right? That's what it comes down to. So if you can just remember that, it's very, very important. So you need to feed those parallel course registers fast enough. You need to move the compute to the data, and you need to pick the right algorithm to address these data distributions. Now, how can you get there? So if you own a GPU, one of these newer GPUs, there's a lot of tools that are available to you. For NVIDIA, here's a little actually talk that was just given this week at Saturn Open Lab Technical Workshop down at Saturn in Switzerland. That was given by my master's student, Ingvild, who's actually was zooming in from Norway in Molde, where her parents live, because she's waiting still to get back to her apartment in France. And as for those of you who know, Saturn is the big particle collider experiment in Switzerland, but it actually stretches into France. So a lot of the people who work there live in France. And it's located in Geneva. So she was profiling this code that's going to go into their benchmarking suite. And she will then also be using this Insight Systems, which is the tool from NVIDIA, and try to also something called Insight Compute. And so basically you get these you run this for CPU, you have the standard tools like Valgrind and Coldgrind, and you can then view it back. These are standard tools that you find hotspots with for any kind of Linux program on a normal PC. And then when you do it on Insight, you have a slightly different command line. We need to give the number of thread blocks, the number of iterations you want to run, and also the number of blocks per grid. And then you can visualize your applications. And here you see seeing the number of iterations. And then you can blow up, an area of interest and see here's one iteration. So what's happening here? Well, this particular application here is one that was reduced to the kernel, doesn't really do much. So most of the stuff is I/O, which is, of course, then means it's memory bound. And really the computations that are over here are pretty small compared to this. But the point is, in this application, they kind of stripped out all the physics. But if you put in the physics against blows up the computation, they would probably be opposite. So you'd probably have less memory traffic and bigger compute. And so here, if you look at that compute kernel, you'll notice that for this particular application, well, you can't really see it in this small slide probably, but this is the floating point unit that's keeping very busy. So this is obviously an application with a lot of floating point numbers, whereas the other parts of the pipelines are not very busy. And then you need to go and see how you can optimize from there, right? This is how you manually look at codes. And you can vary the number of threads per blocks, and I'll give some guidelines to that. You can change the memory utilization. You can reduce the precision or use mixed precisions, so you can use some of those other pipes. And then also you can use sampling information to identify the hot spots. And the previous, last fall, she actually looked at machine learning benchmarks to see which one, were the most suitable. And she will have admit that we ended up saying that MLPerf, the open source one, is one of the best ones. If you want to, I don't know if one of you or some of you are in AI and looking at AI benchmarks, that's a good one to look at. Just want to mention that in case there are more AI-oriented people in the audience. You probably find my basic AI introduction extremely trivial and boring, but at least hopefully my goal of this presentation is to give you a little tidbit each. And the reason that we learned extra much about AI after a grad student already was into that, we had Gavin Taylor from the U.S. Naval Academy visiting us for 13 months back in 2017 to 18. And the first summer he brought over two of his students, midship students, to be with my research group. So that was a lot of fun. To give you a little bit of quick history, there's some parallelism between what's happening in high-performance computing and the AI. In the dark ages, the science fiction writer Isaac Asimov was basically the one describing it. And of course, we started in the 50s also with 1 million bits of magnetic drum that was gunned by Remington Rand. And Navy designed used it in the 60s. And you can see some of these at the computerhistory.org, some nice timelines. Fortran was introduced in the 50s, and punch card came in 1956. In fact, my first program in college in Fortran was one of my first programs was done on punch cards, and it was of course, not very much fun if you didn't have type ahead, because once you hit the key, it punched a hole. And if you hit the wrong key, you had to punch the whole card again. And it was even worse when it came to compiling, because you had to turn it into the compute center, and they may give the result to you back in an hour. And so we debug codes very differently from today. Today, you fix a couple of bugs and recompile. But, well, you don't do that when it takes, an hour or two of turnaround. Then the same time in 56 was also when John McCarthy had this meeting at Dartmouth, where he organized a summer conference, and that's where he coined this term, artificial intelligence. Now, like I mentioned, in the 80s, I did concurrent parallel Pascal. We started, a grad course on expert systems. Was basically that they, you had a lot of if and else systems, and they can sort of analyze it like an expert system. But then in the later in the 80s, you got the fifth generation computing project in Japan that invested 400 million in this time period that sort of, pushed it the envelope. And then you saw there wasn't really, people weren't that impressed with the results they could get out of these expert systems, but you got a big revival when you had better algorithmic tools, kits, and increased funds coming back later, in the 90s. And then, of course, you started to see the AI lab with the elephants. And there was like a nice, interesting quote from Robert Brooks in 1990 saying, elephants don't play chess. So they may be intelligent, but they don't play chess. So again, there was a lot of this expert system bottom up. Notice that Kasparov was, famously beaten by a chess computer in 1997. That was also now top down. And then you got starting to see these robotic stuff like the war dogs and the ROM vacuums. But, the big push when we had enough compute for AI to do model generation. And that's when you see the new era of AI, at least in machine learning. And you also see the Apple iPhones in 2008 putting a lot of work into speech recognition. And of course, today we have both Alexa and Siri and a whole other people listening to AI for us. The IBM Watson also beat someone at Jeopardy back in 2011. And of course, since then, we've kind of been living in the AI era, right? The last several years. And when you've tried to continue to apply AI hardware and AI techniques to supercomputing and HPC and just about every other field you can think of. So the question is, what is really AI or AGI? So there's artificial general intelligence, and there's AI, as we sort of talk about in this talk and elsewhere. Now, the AI is really, some people say it's mostly statistical regression. So your sort of fancy word for statistics. You use it in image and speech recognition. You use it in data analytics. And you also started to use it in autonomous cars like Teslas and other self-driving vehicles you start seeing out there. Now, the artificial general intelligence is machines that really emulate sort of successfully independent thinking of a sort of intellectual being, I guess, and presumably have a sense of self maybe even. And that's a little bit different. So if that's what your notion of AI is, that's not what we're talking about here, okay? Now, there are some pitfalls, okay? We have there's some ethical issues. There's especially China and other countries have used surveillance with AI techniques quite extensively. They are also, how to misuse or misuse the access of data. And then how do you, some pitfall is like, how do you hard code morality into it? And one of the dilemmas in autonomous systems, when you have a car and the car has to decide between, killing the passengers in the car or hitting 3 kids on the street, that becomes sort of a moral dilemma, right? And so that's really hard problems to solve, not technically, but more judicially, right? So, and there are definitely also pros and cons with ANNs. Actually, I think I'll skip this slide in the interest of time. I just want to give you this basic little schematic of machine learning, where you basically have a bunch of inputs, and then each of these boxes You see dots here, or is sort of a weighted sum of some sorts that inside a layer, and then you get some kind of output. And this is the basics for any kind of basic ANN, a neural network. And this one I can see shown with 3 inputs, neurons, a single hidden layer with 4 neurons, and 3 2 output neurons. Now, if you add some more layers to here, you add more hidden layers, that's when you can talk about deep learning. But of course, the more layer you have, the more bigger the data sets you need to make any kind of reasonable guess or train your data enough to make a reasonable model. This ANN here is used for known as supervised machine learning, meaning with known labeled data. There are other types of AI methods there. There's the naive Bayesian, which assumes conditional independence. So it's a sort of a pure statistical thing. You have logical regression. You have also this notion of supported vector machine, where you have included subgradient descent and coordinate descent. And you have this whole field of unsupervised learning, where you use cluster analysis primarily. And so those are some of the classifications of AI that you may run into. I figured I'll take a quick break for some questions. Listening to someone for more than 40 minutes is usually not great, so you should try to grab a drink or Coke or water or whatever you have, and fire up some questions to the Q&A. And I'm sure Carrie here will let me know what you're asking.
Yeah, there is currently one question in here. I'm not sure if you have already covered this. The person asks what equipment you use.
So in my lab, we use a variety of equipment. So I'll show some more slides. When we started, like I said, with those simple, today seems simple, back then looked complicated, graphics cards for gaming. And we still use graphics card for gaming. We just now use the newer Nvidia 3090s instead of, an GTX 8800. And they're, of course, quite different inside. And then for my students in their lab, that's what they were using. We also have, more, server-like, like we have servers with, for instance, one system has 40 T4 Nvidia cards, and that can be used for teaching. Students can log in and run their codes, and, it's a queuing-based system, so they get access to, a graphics card each, and they can try to run it. We even slurm it together with our teaching lab during COVID, since they can't go into this teaching lab. We have, a network of PCs with some graphics cards, and they get shifted to that queue as a spillover from the other one during, peaks of programming exercises. I don't know if that answered people's question. And of course, we have the Dgx2.
Yeah, sorry. The next question is, if you don't mind, can you share your experience on utilizing artificial intelligence and high-performance computing in the healthcare field, like hospitals?
So, so the one application I already mentioned was, when you did ultrasound imaging. And actually that wavelet algorithm we had, like I said, was put into the high-end cardiac scanner at the hospital, actually the same fall, because it was cutting edge back then. And you see a lot of, that's probably because we're all adopter, but, we usually do prototypes. We did one that for segmentation, that, was really good at segmenting, ultrasound. They like to do ultrasound of your brain because you can CT scan your head, but the brain actually floats inside, so it may shift slightly during surgery. And if they're trying to operate, they really like to know where it's shifted to, so they can try to do an ultrasound. And we could do it real time. I had some master students doing this, but, I did. The doctors wanted the codes from me, but I told them they were too risky. And so I sent them to via Syntef, that organization, and had it more professionally coded up. So we more do prototypes. We don't, produce medical equipment directly. Does that make sense?
Maybe take one or two more, because I know you've got other things.
Yeah, one more, so I can say I have a few more slides.
So the one that I've got pulled up here is, what are the current bottlenecks / problems with petaflops computing?
So they have the same challenges, like, the big even your iWatch have. When you try to do fast real-time compute, it has to do with getting the data to the location, right? Location, location, location. And of course, you also have the problem infrastructure around it, especially if you go to exaflop. And because you saw even those big machines at Oak Ridge or in Japan or building in, they take huge amounts of power. And I'll mention a little bit now. So let's say what next. So here's to give it perspective. Here's the big machine room we had for our IBM. That's me. I was the head of the infrastructure back then. So the Power 5 computer, and he gave us 7 teraflops with a proprietary switch. And then we look at today, and we get these, graphics cards. The Tesla V100, which is this in a lot of machines you see today, it has, double precision 7 to 7.8 teraflops. And then you actually have this, actually that's just the DGS station. But if you instead of 4 of them, put 8 of them in a box, you get what you know as the HGX A100 system. And that has not petaflops, but, it takes it out even further, right? So it's, you do get a lot of compute for these petaflops in the graphics card. Like I mentioned, our story started in 2006 with this GE Healthcare project. Here you see some of the older cards we used. So now they have them in the closet in our museum, so museum closet. But we've used a lot of them. But the big thing I gotta say is that we have made a big step forward by having now these big GPUs targeting AI applications. And here you see, a chip of that's in the Tesla Volta. And like I say, the A100 is even more impressive. And the key about these is that they have these tensor cores, this special processing unit, in addition to the traditional floating point units and integer units, that do these small matrix operations. For the Volta, this were in 16-bit floating point with 32-bit floating point answers. But the new A100, they're all 32 in there. They actually have 32-bit tensor cores, which makes them very interesting for HPC compute. Of course, graphics cards are also not the only thing out there. There's the Google's TPU, which is the 16-bit floating point values in the single processor. There's the Intel neuromorphic chip that's on the board. There's the post-K-ARM-based chip that's using the Fujitsu's newest, they call it post-K, but it's the new, something I can't remember. It's named after Mount Fuji. That's what I remember. And we have, of course, quantum computing coming on the sideline using a completely different technology where it's not only zeros and ones, but quantum states, AMD's new EPIC chips. And there's also a lot of special purpose chips. I've already mentioned Fpgas. There are also special AI cards like GraphCore and others that are out there. And here you see that, these banks of these tensor cores, this is that, are also on the chip that you would like to use as an HPC person to get maximal performance. So the first ML paper or machine learning we did was back in 2015, where we tried to enhance the OpenCL, which was the more general code you write, both for AMD and NVIDIA processors. We had a test bench with the Nvidia K40, and we got a mean relative error about as low as 6.1 and was able to find configurations as little as 1% or 1.3% worse than the global minimum. So rather than if you hand optimize codes, of course, the caveat is you need to, do parameterization, right? So, because that's what it's all about. So, a little example is you take a filter, blurring filter, you have your little loops. That's basically a box filter in image CL. And then you try to hide the GPU memory hierarchy. And you go through a sort of standard loops for those of you who, you need to learn a little bit. I can't teach you all of AI in an hour, but, you have to have the code, and you go through how you look at, the source code, and then You do the source-to-source translation, but you also at the same time do an analysis in the parameter space. And then you do an auto-tuning part for some parameter values that give you a candidate implementation for the device, and then execution time. And then once you get these parameter evaluations, you can do, again, a source-to-source tracing and do a best candidate implementation in the end. Now, the kinds of parameters you can look at for the GPU are thread block sizes, which is the size of each thread block, how much work per thread you're going to use, which is known as thread coarsening, how do you access the threads, what kind of access pattern they have, or known as thread mapping. It's also whether you use a special memory for graphics known as texture memory. The fact that it's there, and if you don't use it, of course, that's, I told you close memory is a scarce resource, so you want to use as many of these memories as possible. There's the same thing for constant memory. If you have values that don't change, there's a special memory you can use for those, and you can reprogram your codes for that. There's also shared memory locally on the GPU that, of course, are, good to utilize. And then, unlike many compilers that are, sort of very efficient on the general CPU, the GPU compilers don't tend to unroll for you, so you may have to do some hand loop unrolling. And so when you parameterize your code, you pick some random configuration of these parameters, and then you try to measure them, as a good way of seeing it, and then you get some kind of timestamps, and you try to build this sort of model of your training based on that gives you a prediction of configurations. And then when you pick the best of these configuration, you can then measure them, and out of those, you find the best, and you get your final code. And that's sort of the basics for any of these kinds of AIs for HPC. Then you can basically replace a global mem index plus I. So this is how you write your CUDA code. With the block size is 8x4. Now, at the time, Shuffle couldn't handle unsynchronized threads. I'm not sure that's true anymore. But anyway, this is so we didn't do thread coarsening for this first work. You can also look at how you would do some training for distributing in-mesh shell or OpenCL codes across devices. Let's say you have a bunch of GPUs change every 6 months, so maybe you have some older GPUs and some newer GPUs, and obviously you can't use the same coarsening or thread blocks on older versus newer GPUs, and you can think about the parameterization for that space also done in this kind of manner, and use a machine learning-based load balancing prediction in this case. Okay, and here's some tests we got. You can see that they're depending on what kind of system you have, and these are all old results, of course, on old systems. You can see there's some variance of what these parameters would be best for a given system. Now, we have since then done several projects that are taking this a step further, but also seen some failures, and also have I want to mention here. So, for instance, back in 2018, after that, I had a master's student look at training neural networks in order to predict how compiler optimization flags could be set, and can we use machine learning for that? Because if you looked at the GNU compiler, I don't know how many hundreds of parameters you can actually set on it, but it's pretty impressive, and wouldn't it be nice if you could just pick the right one? Well, it turns out at least the one we trained on, which was the CUDA standard toolkit, wasn't so successful. So not all ML, and that's the danger of ML. It doesn't work for everything, especially if your data sets are either too small or too similar or something like that. They may not give you the results you want. So that's a caveat on that. Another sort of tangential thing we look at is graph-based frameworks. The Kessler Pingali's group at the University of Texas does a lot of great work in that area. And for those of you in NOAA AI, graph algorithms are highly related to AI, right? So without me going to that, there's the Grout, from Pingali's groups, there's the Lux, there's also Gunrock, and now recently, not on this slide, is the BLAST, where you you take a graph develop and sort of try to remap them into basic linear algebra programs. We also did work back in at SE11. We demonstrated how do you do a path, A-star algorithm that we again took it a ground and abstract Zorbris hashing, and this is basically a multi-GPU sliding tile puzzle, which again, when you use a A-star algorithm, is similar to what kind of algorithms you have also in AI. I see I'm running out of time. If we're going to have time for questions. So the last one of the current projects is doing computational microscopy, where we try to sew together several images and light them with an array of lights to get better resolution or bigger aperture and bigger area to look at in a microscope. And so we have had several master students look in this. This is only one of them. There's several others. And we use GPUs to be able to do this more real time. The current efforts, including, like I say, going along the graph-based algorithm, looking at max flow, and also have Jakob Töring, who's faced here, who's doing AI-based auto-tuning framework for HPC, and you'll see more of our papers and publications coming out. We also do benchmarking AI framework and working, like I say, with Saturn I mentioned, geophysical modeling, and we have a little sort of ongoing project on snow simulations. With that, I want to show you this picture. Here you have Thomas, who started with this AI for HPC. You have, and this is at his defense, where you also see Gavin Taylor and several of my other master students and one of my former PhD students. My current postdocs working on top-level sentiment analysis for social media as part of his PhD, so a pure AI thesis, now learning HPC, and hopefully we can use some of his AI knowledge. And like I say, we're now part of this Center for Geophysical Modeling. We have 11 PhD positions out there, so please contact me if you have an interest or know of anyone. And with that, I just want to say it's a great area. It's a lot of things happening. Just have fun with it. It's just new stuff happening all the time, which makes it very exciting. Thank you, or as we say in Norway, tusen takk. And now I'm ready for questions.
Thank you. Yeah, we've got a lot of questions here.
Okay.
I've been looking through a few of them, so let's see if we've got. There was one person who. There was one person who asked, did you already compare GPU cards versus FPGA cards inside the Power 9 environment?
No, I didn't specifically try them for the Power 9. I do have a Maxter FPGA-based system that a couple of my students have tried. I will admit that, most of my master students here in Norway, because they come through our 5-year integrated program, have limited time to do their masters. So, and that's where a lot of my master students to do these kinds of basic tests are. And so far, though that's changing slowly, but very slowly, FPGAs have an even higher, learning curve to do, really high performance compute on than the GPUs. And as you know, some people have even problems parallelizing and doing things efficiently on the multi-cores we have today. And as you know, the new AMD chips have even 68 cores, and how to do those efficiently with the memory hierarchies. FPGAs are very, very interesting. They're very great for a very specific task. If you have sort of one algorithm that's really core to your problem, and if you can encode it into that, it's like basically writing an assembler onto a chip, right? That's pretty much what it is. But I haven't, no, I have not looked at that particular problem.
The next question is, have you ever evaluated performance relative to GPU utilization?
Yes, so that's one of the things you look at. The occupancy counter, in the Nvidia, for instance, will give you some ideas how well you are parallelizing. And there's a whole, I give a whole course on, well, at least a third of my course is it's just the basic of a GPU, and we could probably spend a whole course on really optimizing for GPUs, because you have also these banks of computes inside of the, any bigger card will have several what known as SMs, or, basically a group. They will be grouped, right? The processing units will be grouped, and there will be several of them, and you have to be, that's why you like to parallelize across blocks, so you can separate them out. And then you have to look at your warps. There's still the 32-bit warp that work like a vector machine in some sense. Is a single instruction, multiple thread issuer, right? They had the interesting thing is it has several instruction issuers in parallel, so it can really sort of overschedule them, kind of like a ultra hyper threader. But yeah, there's lots. You want to keep all of those, not only inside of one SMT do you need to optimize. You want to, of course, optimize across SMTs. And if you have multiple GPUs, you have to optimize across cards. And of course, then, as you have several cards, you get also how you optimize is also going to depend on your network. If you have direct connections like an NV switch, like the DGX, it's easier than if you're sitting on the slow PCI Express bus and you really have very distributed systems. So you need to sort of think about how you did that cluster compute in the old days, right? MPI and the whole bit. Did you freeze, Carrie? Shall I take a look at the questions myself, maybe? Yeah, Carrie will let you know.
For a bit, so I'll sort of jump in here. Here's one. How do you handle the timelines of software evolution against the hardware evolution, which seems to be quite faster at the moment?
Oh, I think there's no doubt the hardware evolution is faster. The software can never keep up. That's just, I've never seen software come out ahead of hardware, ever. We're just, and whenever you have a hardware upgrade, there's always the challenges. And I have to admit, this is a challenge on GPU compute, is the drivers, which driver you use for what, given operating system, given, graphics card, blah, blah, blah. Yeah, this is why you want to use containers. You want to contain things, do it more virtually, right? So, yeah, one of the reasons you want to use containers. I can give us a talk on that too.
Excellent. Are there better measures of AI performance than petaflops?
Yes, and this is why we have now the AI top 500, right? So there you want to, not, because, as the AI is more like inferencing, and a lot of it is integer operations, or at least lower flop counts, right? Because they don't really use 64-bit at all. So there's a separate benchmark in ranking suites known as the AI 500. And I can say for benchmarking AI algorithms, you probably should use MLPerf, like I mentioned.
All right. Let's see. Let's find another good one. HPC does fast and accurate diagnosis of diseases with or without using machine learning.
Sorry, I didn't hear it properly. There's some noise in the. Can you repeat
I think what
it?
they're trying to get out, the question is how HPC does fast and accurate diagnosis of diseases with or without using machine learning.
Yeah, so of course, if you have the brute force compute power to do analysis without AI, of course, people, at least in HPC, will claim that's better because, AI is this black box that, could give you trouble. And one of those slides I skipped over was like, what if you have, let me see if I can push this to audience. What if you have outlier, where you, when you, I took this from a TAC talk, and I thought it was a great way. When you have get some data that's not, fitting nicely on the curve. Now, is that an anomaly that you should take, really pay attention to it, or is it as an anomaly that you can discard? And if your AI sort of setup just discards it, maybe you are missing the most important, data in some sense. So this is the danger when you do sort of AI and never sort of is hidden and it's not fully, there's a lot of work these days to make AI methods more transparent. But I'm not an AI person, I'm an HPC person. I can only try the AI algorithms that the AI people provide me and see how well they seem to work versus brute force in my area.
All right. Next one, and I think this might be more in your wheelhouse then. Has there been lessons learned from AI for HPC effort leading to new design philosophy and or new design practices for the design of, and you list them out, GPU, TPU, VPU, XXU design?
So yes, of course, that's why you see these tensor cores, right? Because you have the basic ML algorithms are so tensor core based. They're especially. It's kind of like designing a processor or FPGAing it, right, for AI, and then we try to sort of use it in HPC. So I think that's these tensor cores are a clear example of why they came about was exactly for AI. And I think the question is then, yes, that impacts how we think about HPC and other, compute problems. And just like the graphics cards themselves, with the way they worked, we had already been adapting to, changing hardware, to changing cuts. Like it's a long time ago since we had Cray designing the processors for the HPC field.
Excellent. Next question. You mentioned AI for HPC. Have you used methods such as monitoring HPC performance, looking for performance problems or possible optimization methods?
Yes, I thought that's what we're doing. So I'm not sure if I understand the question. Yeah, we are using both the brute force and also auto tuning. There's a whole I could get in my. I told you. My PhD student and several of my students are working on auto tuning with or without AI, right? So they want high performance. The first thing you should do is utilize libraries. That doesn't matter whether you are in AI or HPC. If in HPC you use the BLAS libraries, whether it's called MKL or actually just BLAS, Atlas, whether you use a very good FFT library that actually auto tunes like FFTW. If you have an FFT in there, don't try to write your own FFT routine. And on the AI side, if you're running on CUDA, you should use CUDA DNN for your basic neural nets, because they're probably coded better there than what you are able to code, at least without a huge steep learning curve. And as you know, those basic linear algebra subprograms that matrix multiply and such, they are usually auto-tuned to the cache hierarchy of the given system. So it's very hard to outperform them. I think I've only had one student in all these years who managed to write a C generator that, spitted out some assembly code that could beat one of them. So there you go.
All right, excellent. Carrie, I think you're back. Are you here to take us through the last few questions and take us home?
Yeah, maybe we'll take a couple more and then we'll finish up. We've already gone a little bit over. So one of the next questions is, how much processor and memory resources are required for auto driving?
Oh, I really cannot answer that question. And also depends on what you mean by auto driving. Tesla has this sort of autopilot mode, right? Also can it handle all these sort of moral situations too? And I really cannot answer that one properly in 1 minute. I'm sorry, or even 5. and it's not my area. I can ask Tesla and Apple, right?
Okay, I think this might be our last one. Is there a quick way to estimate the amount of memory needed as we grow to neural nets?
Ooh. I am not sure. Probably should know these questions, but I don't know it on top of my head. It also, depends. I think the best thing, as I said, for neural nets, if you just do basic ones, is to use the CUN library, and maybe they will, and then use some profiling on that and see, on your code and see how it handles. But I'm sure there's a better answer. I'm sorry. I guess I'm getting tired, so I'm not answering very well. It's really a little bit outside what I do.
All right. Thank you very much. Would like to definitely take this moment to thank Dr. Elster. You've done a great job today. I'd also like to thank Scott for jumping in. I've had a bit of a network problem today, and so he's had to jump in a couple of times. And I'd like to thank all of you for attending. Our next webinar in the Distinguished Lecturer webinar series is going to be in Mandarin and is titled The Environmental Modeling-Based Requirements Engineering, and that'll be given by Jijin. This will be held on April 15th at 2 a.m. Eastern Time. In English, our next webinar will be on using cyber physical technology for speech-language therapy. And that'll be given by Eldon Caldwell on April 19th at 11 a.m. Eastern Time. We have 2 additional webinars coming up in March. Those will be from our Standards Activities Board series, in which we have the Standards for Cloud Federation, and that's on March 16th. And from our Build Your Career webinar series, we have Essentials of Project Management on March 23rd. To register for these, just make sure you go to our website and you'll find them in the same place you found the registration for this one. We'll also have that in our the email that we send out to all of you with the recording of this webinar. Again, Dr. Elster, thank you very much. We've really enjoyed having you speak today.
Thank you, and thank you for inviting me.
All right, everybody have a great day.
You learned a little something.
Yes.